if you do derivative with respect to x1, one minute. There was a small mistake here. If I do x1 dot is equal to, if I do the partial derivative for this one, I'll get k1 plus k2 x1. If you do the partial derivative for this, k2 into x1 and x2 will become 1 plus k2 x2 and x1 will become 1. That means if you do derivative with respect to x1, if you do derivative with respect to x2, the third term will become 0 if you want for matrix A. Then what about x2? Or you can take even this with respect to u. So this will become 1 itself. Yeah. Okay. This will be, if you derivative with respect to u, this will become 1 itself and your matrix will be B1 alone. Similarly, for this one, you will get 2k3 x1. That's it, plus k4 in k4 x1 is x2 is common, normal. For this one, whatever the matrix that you are doing now, suppose you got k1 plus k2 into x1, right? k1 plus k2 into x1. This is the derivative term of x1. For this matrix, here x1 should be constant, which is nothing but my initial value. Actually, it's a small mistake. Here k2 into x2 will come. Here k2 into x1. You can say x1 cap or x1 not. You can say x2 dot and x1 dot. This it's not just this mistake. There is a small mistake like k2 x1 of 0 into x2. Similarly, here you will get k1 plus k2 into x2 of 0 into x1. You'll get a matrix like this. So a small mistake I made there. A small correction here. So this is how you have to consider this one. And this is how you have to consider this one. But actually x1 in initial values and x2 initial values will be there. You can say Control S. Okay. The MATLAB. See here, initially the state values I took like some 2 and 5. These are my initial state values. And what are my main parameters? State parameters, I took the states. What are the states that I have? X1 and X2 are my states. And what are the parameters that I have? This is my parameters. I'm just considering this as some function. Now, what I have to do is, and even I have to place the values. If you take this is the states and parameters, your states are x1, x2, your parameters are your constant matrices. Whatever that are there, that are constant matrices, but in symbolic form. So that is your state part. What about state part values? I just have to place those values instead of that. So at a later stage, I'm going to equate this. What is my control? My control is your input u. Now, this is my derivative term x1 dot is equal to a1 x1 plus a2 x1 x2 plus b1 u. This is the actual input function I gave now. This is the actual input function. A1 x1 plus a2 x1 x2 plus b1 u. A1 x1 plus a2 x1 x2 plus b1 u. What about my x2? It is k3 x1 square plus k4 x2. A3 x1 square plus a4 x2. This is my x2 dot. So I'm defining this again as some matrix. So it's a column matrix. Simply instead of making it two separate things. I'm considering both of them in a single matrix for matrix representation. There is some command called Jacobian. What is this Jacobian do? It will find the derivative term of that. So B Jacobian. Sorry, A Jacobian is there. If you type Jacobian command, then you have to give what you want to do and what are the state variables. Suppose if you see state nonlinear, these are the equations that I am giving. A1 x1 plus A2 x1 x2 plus B1 u. That means this state's nonlinear function will have these two equations. Okay, comma, in this one, what you want to make the derivations. I mean, whether A1 is your derivative term, I mean partial derivative term, or A2, A1 or X1 or X. There are so many terms, right? All these are symbolic values only. But what are your states actually? So my states here are X1 and X2. That already have defined my states are X1 and X2 here. So what does the Jacobian matrix do? As it has multiple values, among this, it will take x1 and x2 as your states, and it is going to perform partial derivative format. This subs is actually the symbolic representation. That means whatever the function that you have, suppose A Jacobian, whatever the function that I have. So system parameters. What are your system parameters? Your states comma parameters. That means all these values. These all values will be considered, state parameters will be considered as symbolic form. If you type subs, you can see. If you type subs of, if you type see this, it is actually the representation of older ones with the new ones, and it is going to make them as symbolic form. So here only S is like symbolic form. If you click more help, it is like symbolic substitution. You understand, right? That means now I have a different function here. Whatever the Jacobian matrix performed, this AJ is in symbolic form. Okay. Let me show you that AJ is in symbolic form. As I said, A1 plus A2 x2 plus A2 x1. This is how it is going to give the symbolic form. Like it will have a partial derivative term like this. Like if you have x1, x2, f is a function of x1 and x2, then Jacobian matrix will become f with respect to x1, which is partial derivative, and f with respect to x2. This is how you will see the partial derivative. Here, there are two equations. One is x1d and x2t. So there are two equations. These two we are going to get the output here. Similarly, for Jacobian matrix B, I'll get it in same, but I think a constant value will come. B underscore J, only B1 will come. Because you are derivating U with respect to U, you'll get 1. So you'll directly get B of J as B1. So this is my matrix B. I'll use this double because actually I have substituted these values. A is not like, now see here, AJ matrix, this is my values. These are in symbolic form. Using this symbolic form, and all these are symbolic variables. Now whatever the values that I have, it is going to replace them. State parameter values are some constants. See, parameter values, they are some constants. So these constants will be updated here. I mean, whatever A1 is there, instead of A1, it will be taking as minus 79.86. So similarly for A2, it is going to take some minus 0.35 like this. So in A matrix, you will get it as a constant value. If you type A, you will get some constant value here. Is it fine? Similarly, if you type B, actually I have run this simulation. You can start running this simulation. You can take 5 minutes, 10 minutes of time and tell me the system. I just want you to simulate and check the system. Remember, for a nonlinear system, when you are linearizing from nonlinear to linear system, initial values are very, very important. How can we use dspace using MATLAB? Whatever the code that you have now, it will have some embedded tool. Like, actually I didn't install in this. There will be something called embedded system. It will have a separate entity for that. Can we use dspace with MATLAB? Yes, obviously you can use dspace 1104. I mean, whether you have PC slot something, PCA slot, if your computer has, then you can go for it. There are some, I mean, older computers, newer computers, they have some disadvantage. Is any library required in MATLAB or dspace? Yes. Once you install it, there will be a separate tool, I mean, separate extension for that. You can go. Instead of dspace, nowadays I can recommend you can go for a speed goat. Speed goat is somewhat more compatible with MATLAB. Sometimes dspace with MATLAB, it won't be proper. You have to go for the dspace software only. Yeah. So do you have the DSP code for pulse generation using SPWM? See, when you have Texas Instruments things, why you want to go for DSpace? For Texas Instruments, you'll get for 2000. DSpace something 10 lakh or 14 lakh. When you have your Texas Instruments incompatible with that, go for that. Don't use DSP. DSP. Oh, you have DSP code. Okay. I thought DSpace code. You want this code, you can generate it. It's not a big deal actually. We'll see in the next workshop if you want. I mean, we will see. I don't know whether everyone can install CC Studio and all. Actually, we thought of presenting with hardware in this one, but we don't know about that everyone whether they have that controllers, everything. If you just see that, you may feel like you got it, but you actually deploy the program only, then you can understand the system. DSP means you're saying Texas or BeagleBone? What is it? Sir, I have a nonlinear equation of fourth order with variables. Is it possible to linearize using Jacobian command, sir? Now I'm going to show you something here. Sir, you can linearize. If it came into linearization, yes, you can go for it. 28335, 355. Sir, actually you have to see what I did here is it is like x1 into x2 term is there. If I derivative this, I got that. but you are saying that fourth order. First, make sure that you are going to convert into state space representation. If you can convert it, I mean, a single derivative order, not fourth order. If it is fourth order, I don't know how we can do that. Yeah, first, if it is fourth order, you have to convert into first order. If it is first order, are you saying four state variables or fourth order means x1 derivative? I mean x1 triple dot, x1 four dots. If you have that fourth order, then you have to expand it. You have to make into what you call uh, first order system like this. Once you get the first order system, okay, four state variables. Yes, sir. Any number of state variables. I think mostly you people may have an induction motor or PMSM models. Yes, for them the speed, current, sometimes they will multiply. Sometimes flux speed they will multiplied. You can use this linearization tool over there, and you can do the analysis on your own. There are some state variable representation of your motors. Yes, you can use that. I gave this model because of that only. This was similar to DC motor. Okay. So let us go for this. Now, after running this, you have got A matrix, B matrix, C matrix, D matrix. Okay. Let us open a simulation on the grid integration. I think I didn't open that. I'll go for new. I'll create a model. I'll save it as non-linear. Okay, there is something called state space. In this one, first you define what is your matrices. Go to model properties, callbacks, initial function. Define what is your A. What is my A here? Minus 79.99, or you can write minus 80. Minus 80 space minus 0.0135 minus 0.0135 or 135. Okay, 0.135 135 colon. So next column it is 3.51 space minus 0.5677. Actually, I have changed the values. You observe those values. I changed these values. Earlier, if I do that, I just got a single constant value. Obviously, you will get infinite rising thing. You won't get a proper value. Define it. Next, define your B. What is my B? It is simply 6. Okay, let us take 6. Or I'll make it instead of B, instead of 6, I'll make it 1 itself. Try to have complexity. So let me run this. Okay, it was done. B is equal to 1. C, as I said, I need a matrix C. I need only the second variable. So you can give 0 space 1. My D is equal to 0. Okay, you can apply. Okay. So this is my state variable representation. Apply a step input. Connect it. Connect a scope to that. My system is actually unstable. This is my input function. You can see it's somewhere around 9,000. Sir, B as a matrix. Didn't I define as B as a matrix? Yeah, B is a matrix now. sorry. Yeah, here's a matrix. It is 1 column 0. Thank you, Shivaji sir. So you can simulate this. Again, I got an unstable system. Okay, then I'll do one thing. I'll manipulate these values. Right click, model properties, callbacks. Values, actually, I've got it. If you randomly give, it may not work. Okay, let us check this A matrix. If I see my A, it is minus 79, okay, minus 80, minus point, it is 0135, 0135. Somewhere this one is 335.1 minus 0.5677, B0, okay, apply, okay, for an input of 1 at one step. Still my system is unstable. I think I have to modify that equation. If I give this, then it will not work. I think I have to add an extra term. Let me add an extra term here. So if I see the terms, then I'll copy the values. Actually, I'm not finding that function where I placed it. Okay, it's like, I'll just tell this part tomorrow. Actually, what we'll get is you'll get some, it's actually getting unbounded. If you get some value here, so this is the linearized equation. Now, you can write this non-linearized. For this linearized equation, whatever the input that you have, suppose you're going to change from 0 to 1 value. I want to track it exactly. So suppose if I'm giving 0 to 1, my output may reach some value to 0.3 or something. But I want my output to be at 0.5. Obviously, what you have to do, you have to use a sum block and minus, and you have to use a PID controller. Then you have to make it PI controller, apply, okay. Connect this. Connect it here. And I need my output to be connected here. Then you can tune these values. Actually, now you may not get the tuning properly. So it is saying P0 I 78.79. . if you see here for this value, actually my system is non-linear, but I'm trying to apply a PI controller to control the system. Though it is unbounded, you can make it bound by using a PI controller. I'll say what is my P value? P value is 0. My I is 26.11. So you can go P is 0. I is 26.11. Click OK. So it has to reach that 0 to 1 value. Let us simulate this. Okay. What is my second one? Second one is my PI controller and first one is my output. See, the PI controller is becoming nonlinear to make your system bounded. Let us see this. You got it right. Though your system is unstable, this is actually, I didn't do that, but it happened. Though my system is unstable, you can apply PI controller if you have a linearized system. I forgot. Yeah. Out. Okay. So this is how you can see. At point 1, I have applied a step, and this is the response of my system. If I use a PI controller, this is the output of PI controller. So this is how it is. But if I don't use this PI controller, and if I directly apply that system, let us use a manual switch. We'll connect this, delete this, connect here. I'll delete this. I'll give it here, and I'll give it here. So if I simulate this is my input. So actually this is my output, right? Actually the output is highly unstable. It is becoming nonlinear for a given step input. So this is my input 0 to 1. And if this is the output of my response, it is actually becoming nonlinear. So what I do is I just connected that in some loop, and I've used that auto tune button to get that some response. So if I make it in PI loop instead of input, now let us see the same input with respect to output. Yeah, you can see my input is 0 to 1. My output is also tracking from 0 to 1. It is approximately, it is trying to maintain that value. You got it? So this is for my linearized form. If I have got this for linearized form, let us do for nonlinear system. So whatever your nonlinear system you have, so let us use MATLAB function. In this MATLAB function, how many outputs you have? You have outputs 1, but how many inputs? You have 1 input. You have to write an equation. This one. You have to define that matrix. Let us define those values like A1 equal to what is A1, A2? I have to find now. Actually. Okay, we'll see now. I just want to find this A1 because A1, A2 it's different, right? Minus 79.99 you got. This is like after the multiplication of that values. So for this linearization, what I thought of doing is now I'm writing a nonlinear function only. I am not going to write a linear function. So for this one, x1d and x2d, these are my values. Control C. Let us leave that value first. We'll write this equation. So now, so I need two functions. One is x1. You'll get x1 dot x1 dt only. You have control C. You can make it control V, comma, control C, control V. This is a closed loop, and your input function is U. I think x1, x2 also you're getting it. X1, comma, x2, comma. You're going to get a system like this. Now I have to define A1, A2. So let me approximate the values. Actually, this one is like A1. If you see that, A1, X1, sorry, A1 into X1 plus A2 na. And at here, A2, A1, sorry, A1, we'll delete this. Okay, let us assume that these are the values itself. I'm taking these values or A1, A2, A3, A4. Let me write it as A1 as minus 79, minus 79, comma, what about my A2? A2 equal to, I'll make it something minus 0.3, minus 0.3, A3. A3 12 by 2. Let me take 6. A4. A4 is something 4.5 only. Let it be 4.5. 4.5. Now B1 is 1. Okay. Now what I have A1, A2, A3, A4, everything I have here. So I've written this form. Now it is actually non-linear form only. Let us delete this. And let me save this, control S. So it's like non-linear, it is saved. Now see, this is my function. It is non-linear function only. Now what I have to do is I have to use integrators. So you can use integrators here. So initial values, how much I took last time? There I took the initial values as 0.1 and 1. So here x1d is your 0.1. What about the initial value? It is 1. This x1, now if you take this is x1 dot, after integration you'll get x1. So this you can give it here. If it is x2 dot, after integration you will get x2. Now here is your u. If you give u here directly, what is your output? Your output is x2 itself. This is your y. Now this is my output. So let me connect scope and we'll see this response. Simulate it. A4 is equal to, sorry. Let me simulate again. Valid MATLAB function, line 5, column 7. 4.51. What is the problem? Correct only, no? So it's actually becoming unstable. And whatever the PI tuning that we have done, let us delete this. Let us connect this part. We'll copy. We'll take it here. Whatever the output that we have. So this is your input. Okay. Whatever. Control Z. This is the output. So whatever output we have, that we'll give it here. I think I missed it somewhere now. That has to go to you. You can see the things. So this is the step response. At time it has to go to 1. If it works, it is good. If it doesn't work, then you cannot go for Jacobian representation. So let us run our output. It didn't work here. That linear approximation, I think somewhere I did. I mean, if you place the values properly, na, it might come sometimes. 0 U. I don't remember. It's becoming abnormal. So what is the problem here means you cannot apply a linear matrix representation. I mean, this is going to violate. So though you linearize your system and you find the PI value, sometimes this PI, even for this nonlinear system, it may work. But here it didn't work. If you try to place the proper values, I think you may get it, because I got once, but now I just changed some random values. So that's why I'm not getting it. But if you have proper values, you place them here and try with this nonlinear system. You may get that output, you may not get the output. If you don't get it, then use Lyapunov function theorem. Lyapunov theorem. If you use Lyapunov, then definitely you'll get that output. Okay. Am I clear in this? Are you clear in this? See, that linear approximation, whatever we have done, it is able to track your output properly. But in nonlinear system, though I have linearized it, it may track or it may not track. If it tracks, it is well and good. If it didn't track, then you have to approach another method. That's the only way. As I said, you can go for Lyapunov stability theorem, or even you can go for Popov stability. You can assess that function, then you can go for this. Is it feasible to fabricate? You can deploy MATLAB function in embedded systems. MATLAB function is allowed. If you can write anything in MATLAB function, it is well and good. But some blocks, like some PI blocks, they will not be allowed. They will have separate PI. Those blocks only you have to use. They will give some inherent blocks. Those you can use it. But MATLAB function you can use. Yeah. This is for this non-linear system. I just gave you one thing. You can search for this Lyapunov function analysis. So there are a lot of videos. You can search for that. You can go for it and you can do. This is actually the representation of a DC motor, because you have only two variables like current and speed. So you will get this format and you can do the analysis. The next one, it is phase lock loop. In grid connected inverters, we have two main things. We have to control the, we have to control our, we have to control the parameters like DC voltage regulation, or we have to control the output voltage or output current based on the requirement. But for all these things, there is something called tracking of the system. When you are integrating any of the inverters into the grid, you have to think of three things. Let me share another one. A minute. if you see, if you connect any inverter setup or anything to the input source, if you connect it to the grid, if you connect it to the grid, you have to make sure that you are going to meet three things. One is voltage magnitude, phase, and frequency. All these three things are very important when you are integrating your system. If voltage is not synchronized, suppose after this inverter, if my voltage is like this, but your actual voltage generated by the grid Vs, assume that it is somewhere like this. At the same instant, it may be like this. Let them have different magnitudes, that is fine. But if you are adding this, the potential difference will become, it will become very large. So if you take Vs minus Vt, you'll get more larger value. You'll get more larger value. And even if there is a frequency deviation, suppose this is your Vs, and whatever the inverter output Vt, if it is at different frequency, and you are integrating that Vs at different value, you can see at some part it is okay, but at later on, you are going to create unnecessarily large phase differences, which is again not allowed. So you have to make sure that three things like your magnitude, phase, and frequency are synchronized. To do this, earlier I told you one method, like if all the phases are balanced. In SVPWM, at the time of SVPWMs, I told you one method. What you do is, if it is a three-phase network, you have ABC, you are going to convert this ABC to alpha beta. ABC to alpha beta. I told you once, like your A phase, B phase, and C phase are like this. So at one instant, your A phase will be at maximum value and B phase, C phase will be half. Actually, in three-phase balanced system, na, if one of the phase is at maximum value, the other two values will be at half. So that if you add that all the three at that instant, suppose A will be Vm, then B will be Vm by 2 and C will be Vm by 2 at that instant. I'm not talking with respect to time. I'm just talking that magnitude alone. And if you add all these three, it will be like minus Vm. You'll get minus Vm by 2 and minus Vm by 2. If you add all that, you'll get the sum 0 for a balanced one. What I want to convey here is, at a moment, these phase shifts, whatever three phases that we have, at one point they may have maximum, the other point they may be some half. At a later stage, its magnitude is going to increase and decrease in the same line. Okay. Similarly, in this line, this is going to increase and decrease. What about my C phase? It is going to increase and decrease. And at all the times, these three are having a phase shift of 120 degrees symmetrically. That means it is A, it is B, it is C at all the times. A, B, C will have a phase shift of 120 degrees, but only their magnitudes are going to change. Their magnitudes are going to oscillate at those points. So with some manipulations, like a three-phase system, which are displaced by 120 degrees each other. So I'm going to transform it to two-phase system, which are displaced by 90 degrees. So what happens now? If I do some matrix manipulation of this three-phase, so I'll get two phases, alpha and beta. These are at 90 degrees to each other. What happens as A, B, C are going to vary with respect to time? isn't it? My A magnitude, it is going to vary, and B magnitude, it is going to vary, and C magnitude, it is going to vary like this. They all the three are varying with respect to time. Obviously, alpha beta terms also, what will they do? They will also vary. At one point, alpha will become 0, B will be maximum. At one point, alpha will become maximum and B will become 0. So B will become 0. It's like this. Alpha will be maximum, B will be 0. At one point, alpha will be a bit more, beta a bit more. I mean, alpha will reduce, beta will increase. At one point, beta will have maximum and alpha will be 0. If you observe, the angle between them is not going to change. It is 90 degrees only. But what happens with respect to time, the amplitudes are changing. Like alpha amplitude is changing and beta amplitude is changing. So if you know alpha and beta, you can find theta instantaneous value, which is tan inverse beta by alpha, because alpha and beta are always orthogonal to each other. That means alpha plus, they can form a matrix like this, alpha plus j beta, and alpha is a function of time, beta is a function of time. That means v alpha of t and v beta of t. These two are displaced. Suppose if v alpha of t is something cos omega t, then your v beta will be cos omega t minus 90. So it will be like this. So they are going to vary with respect to time. As you can see, you can find theta from this. This is one method to find theta. If you can find theta, you can simply multiply sine theta, which is varying, like this theta is a omega t now. Because alpha beta are varying, obviously your theta is going to vary. Here we have to use 2 tan. Sorry, 8 and 2. I already told this function. So your omega t is this one. So if you give this omega t to some sine function, it is going to track your actual output. Okay. It is going to track your actual output. This is one method. But there is one more thing called phase lock loop. Whereas finding theta is not, theta is equal to tan inverse beta by alpha. This one is not a phase lock loop. It is a basic method if all the phases are balanced and they are having uniform magnitudes, there is no jerk in them, then you can find the theta from them. But this is not a very good method because the theta representation is always a specific constant at a time, and it is dependent only on alpha beta magnitudes. Suppose if there is any disturbance in this VA, VB, VC, then the theta that was tracked, it may mislead your output. So this is not proper. So they are going to develop a technology called phase lock loop. PLL represents phase lock loop. What does this PLL have? This is the alternative. PLL is an alternative for theta representation. Theta is a basic mode. Now PLL is somewhat advanced. So in PLL, what they do is they have something called voltage controlled oscillator, low pass filter, and some multiplier. What they do is here you need theta, or you need sine theta. Whatever your actual function is there, it has to track this. In this voltage control oscillator, you'll get two things. One is theta. Actually, it is sine theta you'll get. One is omega. These two functions you'll have. LF represents low pass filter. What we get is U is actually some Vm sine theta format. Let us assume this. Okay. Vm sine omega t. Assume that this is my current tracking of the network and I am giving it to this. So this one is also something like sine theta. Actually, this output has to be, assume that if it is theta, there has to be some sine block. but that is inherently there in VCO. I mean, sin theta terms will also be there in that VCO. The bottom two things now, whatever that was there here, these two are the voltage controlled oscillators. Okay, that means they can generate your theta, they can generate your cos function. So what is it is, you have Vm sin omega t and sin theta. Assume that Vm is 1. So you have sin omega t function on sin theta. If you multiply sin A, sin B, you'll get two terms, cos A minus B minus of cos of A plus B. Isn't it? That means here omega t minus theta. What about cos of A plus B? Omega t plus theta. Assume that theta almost equal to omega t. That instantaneous theta is almost equal to omega t. Actually, some sine terms you can say. In terms, so you can see that if it is almost equal to omega t, this is a constant. What about this term? There is some, it is all omega t. There is some extra term called cos 2 omega t, which is double frequency term. Now, I want to make this theta common error. So what happens is, here I'll get two terms. Let us assume that some function I got like sin omega t minus theta and sin omega t plus theta. There is something called low pass filter. What does this low pass filter do? Whatever the frequencies, amplitude, whatever the frequency is less than this cutoff frequency, it will simply allow them, and higher frequencies it is going to eliminate. So I will choose this low pass filter such that this double frequency term is going to eliminate. That means this omega c somewhere I'll choose, and this 2 omega terms will come somewhere here. Assume that it is almost less. That means it is almost mitigated, and you got this theta. I mean the sine of theta minus theta. Okay. What happens? I mean, it actually error. This is small error. If you send this error, whatever error that you have, if you send this error through PI controller, you will get some constant, because this is some constant, sine of theta minus theta 1, sorry, sine of theta 1 minus theta 2. For small value of theta 1 minus theta 2, it is approximately equal to theta 1 minus theta 2. Isn't it? So this is my error. This is my error. This error I'll send through some PI controller. So this is some constant at a moment. So what will I get after PI controller? I'll get some constant that you consider as omega. That is not theta. Why? Because you're getting some constant here. Now this you have to integrate like this. As you can see. So this actually assume that, ignore this. I'll tell you what is the significance. So here I'm getting that delta omega naught, which is the output of some PI controller. Some PI controller is there. It is giving an error output of omega naught. This I'm going to integrate. As you know, if I'm integral 1 dt, I'll get some time t. So if you integrate between some limits, so you'll get some value between that. So this phi is actually a function of time. Am I fast or am I slow? What is it? Can you able to understand that? Little fast. Okay. Mm, See, what terms that I will get here is, if you multiply two sine terms, you have sine omega t term and sine theta term. You'll get two terms here. Okay. these two terms, if you multiply, you will have some double frequency term 2 omega t or sine theta plus omega t term and sine theta minus omega t term. If you pass both of these to low pass filter, what we get here is we'll get that low pass term only, that theta minus omega t. So this is like for a small angle, assume that these two are very near, then for small angles, sine theta can be approximated to theta itself. So this will be approximated as theta minus omega t, which is your error. I mean, this theta has to be omega t or omega t minus theta. This is my error, isn't it? Now this error, whatever error, that I will pass it through some PI controller and I'll get my reference value. This reference, as it is some constant, you'll get some constant omega. So this is your delta omega actually. I'll tell you why it is delta omega. So this change, but I don't need a constant. I need some function with respect to time. So if I integrate this, I'll get this theta. Okay. This theta, if you pass it through some cos function, you'll get that y. So this is your voltage control oscillator. So once you give that y back here, it is going to track that. That means slowly, it's like feedback. Your theta is getting upgraded for every iteration, and based on omega t, if it is 0, whatever the final value that you got theta, that it is tracking your input function. Whatever omega t that was there, that will be equal to theta. This is your tracking. That means if you can find theta, that means it is your PLL output. Once you get theta means by multiplying with sine function, sine omega t or cos function. Suppose whatever theta that you got sine theta first one, the second one like sine theta minus 2 pi by 3. You can simply multiply this and sine theta plus 2 pi by 3. So you can find that function and correspondingly you get like m sine. This magnitude we'll see later. So if you do that, this reference is going to generate whatever the sign reference that you got, it will be in phase with your grid. So it will be in phase with your grid. Once it is in phase, then you are going to compare, then corresponding pulses is going to generate. The fundamental will be in phase with your voltage. Even this is also in your hands, how you want to generate. If you want to inject real power, obviously, suppose whatever the network that you have, it is your Vs and it is your Vt after inverter. If these two will have some difference, it is 0 and it is theta. If these two are having some difference, then you are going to inject a specific amount of real power into this. If you want to inject reactive power, you need to change magnitude. That Vt magnitude you have to adjust. That means there should be difference in terms of magnitude, fundamental component magnitude. If the magnitudes are different, then you are injecting reactive power. I mean, based on the magnitude variations, the reactive power flow may change. And based on the phase difference, the real power may change. I'm just telling you, this finding theta is not only of this output. You can get theta reference from somewhere else and you can add that theta to this. If you add that theta, suppose let us say this omega s, whatever the inverter we have, after let us say that some filter. Let us take some filter. This is my terminal voltage of my inverter. This is my Vs. Here it is some 0. So if I directly give this P theta here, then I'll get 0. But if I add manually to this theta some value, some theta dash, that means because of this phase difference, it is going to inject real power. So this extra theta that you will get it from some power reference. So I'm not going to teach that. I'll just teach you a very basic one. I'm just explaining you how you are getting the theta now. Okay, this is how your phase lock loop works. Discard this. So much time. Okay, then I'll do one thing. I'll directly run the simulation. Yeah, we'll get it now. So this is the system so far we have discussed. I mean, I'm just explaining you the operation of phase lock loop. If we see the MATLAB function, it is somewhat similar, but I'll tell you what it is. The MATLAB function, PLL. So suppose this is my three-phase grid. From that, I am measuring my VABC. There is something called VABC to alpha beta 0 conversion. There exists a direct block. You can actually use this, or you can type a code that I already told you in during space vector pulse width modulation. So you'll get alpha beta. Once you get alpha beta, here itself you can get theta. That theta you can directly give here and you can generate. This sine function, this cos function. That's the only thing. In PLL, what we do here is, someone raised query? No. Okay. What we do is, we will convert this alpha beta to DQ0 reference. What this DQ0 means, let me try. So alpha and beta, they are orthogonal to each other, and DQ also, are at right angle to each other. So, but what happens here, alpha magnitude is going to vary with respect to time. Like it may go at maximum, then it may go reverse direction. Similarly, beta may vary like this, or it may go maximum, it may go reverse direction. But what happens to DQ conversion? In DQ conversion, again, there is another thing. In DQ conversion, the D magnitude and Q magnitude is not going to change. That means this D and Q terms, they will be constant. Then what about this time varying quantity? They are going to move with respect to time. Okay. That means with respect to reference, this DQ right angle, which are having some magnitude, let us say that it is having some 8 magnitude, it is having some 4 magnitude. These magnitudes are not going to change, but this perpendicular vector is going to rotate with respect to time. That means after some time, this 8 magnitude will come here, and this 4 magnitude will come here. So this is how your DQ reference. Whereas in alpha beta na, the alpha beta will be always in this straight line. It is not going to move. It is not going to move like this. It will not move. It will be always here. Similarly, alpha will always be here. But their magnitudes with respect to time, they are going to change. Whereas in DQ reference, the DQ magnitudes, whatever D that we have, D and Q, their magnitudes is not going to vary. That means magnitudes are constant. But what happens? They are going to rotate with respect to omega t. The derivatives you can see in electrical machine theory by Bimra, not electrical machine theory. Generalized theory of electrical machines. Generalized theory of electrical machines, Bimra, you have that ABC to alpha beta and alpha beta to DQ. Parks and clocks transformation. That you can see the derivation of them in there. Now you can see in order to do ABC to DQ conversion, you need to take omega t separately from that. So what I do is I randomly give some omega t among this this is DQ0. Now let us see how we can do that. Suppose this is alpha, this is beta. So what happens to my DQ? With respect to alpha reference, let us assume that the DQ reference, this is DQ. These are variables. I'll write it as variables. These are constants. DQ will also be at 90 degrees. This is DQ. If I make my Q value 0, okay, if I make my Q value 0, then it is completely aligned with the D axis alone. But if you can track this D, you can find omega t, isn't it? So you have to make one of the reference 0 to get the entire thing aligned with D alone. So if you make Q 0, if you compare it with Q, use a PI controller, some tuning value you will get. I'll tell you how to tune it again. So if you just give this to PI value and use some integrator, because here I'll get delta omega. What I'll get here? I'll get delta omega. So D aligned with which parameter? Omega t. That means actually there is DQ na. How can you track this omega t? If I make this Q0 na, what if I'm going to track? If I make Q0, that means it is omega t line only. This is omega t. It is omega t line only. That is how we'll make one term 0 and we'll make that tracking. Yeah. So here I'll get delta omega. Here I'll get theta. Yes. This is simply sine function, cos function. If I open that, it is simply minus sine of u1, minus sine of u1. If you open this, it is cos of u1. These are the common representations. If you see that here, so you can either use minus sine of u1 or cos of u1. Okay. So once you do this, let us observe for my PI tuning value, whether whatever the grid value that was there, here is my ABC, right? So this is my ABC and I want to let us take only one phase, alpha phase. Here is my alpha phase and it is my sine function. Minus sine function you have to multiply. So if you simulate this, it has to be in synchronized value. Let us make overlap. I 1. Okay. Actually, my laptop is struggling, so I just made that point. If you can see, okay, actually it's magnitude now. I'll do one more thing. I will add a gain. What is this? Something 565. Let us make 565 gain 1 by 565. You can simply place it. You should track that. You can actually see this yellow line is my actual alpha. But if you see how the PLL is tracking, You can see that this is my alpha and my PLL is tracking like this. So once you can track that PLL, then you can give that, it is like a clock function input to your sine function. Clock input to your sine function. Once you give that clock, then you can exactly tracking the grid voltage. Okay. What's the time? 7. Okay. Shall I speed it up? Did you understand this? If you want, you can try now. Sometimes what we'll do here is we'll use the low pass filter, but here the PI controller itself is going to act like a low pass filter. That means there is some function there. So this function is going to act like a low pass filter. And at the same time, it is going to use it to minimize the error also. Now, how to tune this? We have to use a function. Yeah, and one more thing, I forgot to tell this. Why we need omega n? If you don't give any initial term, this is called feed forward term. Whatever omega n you have, this is called feed forward term. Yeah, this is called feed forward term. If you don't have this, if you just got delta omega naught, your output is always 0. If you give this constant omega n, which is your 2 pi f, then initially it is going to take and then it is going to respond the system properly. Now, how the transfer function you have to find? Let us see that. It's a very basic formula only. You have a simple 1 by s function. That is the only term you have. And you have your PI controller. Let us check it whether we can tune the things here. You can open this. You have the system. You can click on tune. This is how I got my response. As I said now, after dq0, these are some constants, but you're taking omega t from them. You can see this derivation in Generalized Theory of Electrical Machines by P.S. Bimra. So it is like you are applying a step input to PI controller and you are observing the system response. It is just only one sine function. It's a simple function only. And you are going to tune that value. So if you tune it, this is your response. So if you want faster, it's not going to vary much because it's just a basic integrator now with some value. So there won't be much abrupt network there. Okay. So we want around 1.2. It is saying something completely there, but we'll get tracking faster only because it is a closed loop. And what are the values? Something like we got some different values. It is time domain, parallel PI, minus 0.0174, update block. Let us click this. So we got this. Let us try with this now. Actually, I forgot to test this part alone. And let us simulate. Yeah, so this tuning part didn't work here. Actually, it is completely out of scope. It is not at all tracking. Okay, give me some time. Actually, these are values that I took block. If I give this 15,000, then it is tracking properly. Okay, I'll tell you in the tomorrow session how we can tune this PI. Okay, Actually, there is one more block that they consider here as first order derivative function, like transfer function. You can type transfer function. This transfer function will be approximated to, whatever the tracking system. You have to write it is tracking some e power minus. So here we're using PI controller as low pass filter, right, sir? Yes. In this network, it is actually working like that. But in fact, I'm going to use that transfer function actually. That low pass filter I have to use, not just this 1 by S only. If you properly do that now, 1 by S, and this is like low pass filter. But for this, there should be some delay because you are using bridge converters now. So there has to be some exponential function of some TS minus TS. So you'll get some function in the numerator. Actually, the K, some K also will come. Some K into this function. Denominator, there is something called tau. So apply. Okay. So you have to use a function like this in series with this to track this network. In tomorrow session, I'll practice it once more, then I'll give you. Okay. For the time being, let us wind this up. So this is how your PLL work, and this is how what you call your linearization of the network. It has disadvantage and advantage. Similarly, your PLL, you have to properly tune it. If you don't tune it properly, it will not work. But even in hardware networks, there exists one PLL block, this three phase. Whatever the PI tuning that they have done, this 180, 3201, there is something called adaptive block inside this. If you press Control U inside this, so there is something called adaptive gain control. So what does it do is, it is going to control that gain properly on its own, and it is going to update that. So once you get it, then it's like it will tune the things properly. This is called adaptive control. Like your your gains are scheduled. That is called scheduled gaining. You can say that. Even where you use adaptive control now, for a given parameters, you may get some system, and for that system you have designed PI tuning. For this PI system, it is running your plant properly for some years. After some years, maybe some of the parameters drastically changed. This PI may not work at that time. Then what they use is they use adaptive controlling. Like they will modify the KPKI value on their own, which is called adaptive system, or you can say gain scheduling. With that, they will adjust on their own and they will give you the corresponding output properly, even after some time. But even adaptive system has some disadvantage. So nowadays, like as someone has model predictive control, sliding mode observers, they are famous in these days. So this is for PLL. If you see the next topic, did you get the PLL concept? At least concept you got it right. Yeah, thank you. So this is how a PLL work. Now, see, let me sharing line row. So far, we have understand how is the PLL, how a PLL work. Now, assume that now I'm tracking the data properly. If you see here, If you see here, you have a half bridge network, a single leg half bridge network that I am integrating with the grid. Assume that I have PLL output. That means I'm tracking my VS. This is just a filter, a simple filter. Now this is my VT and this is my VS. Now what I want is I want to inject a specific amount of current, which is called reference current, into the grid. If I want to inject a specific amount of current, I want to know the function. In general, this is your VT, this is your VS. This equivalent switching representation I'm not going to bother. What I do is, for a given modulation, whatever the modulation that I have, that I'll multiply with VDC. What will I get? VDC by 2. I'll get MVDC by 2, which is your moduled output. This MVDC by 2 is nothing but your VT, terminal voltage across your leg, or terminal voltage of the inverter. If you subtract VT minus VS, if you see, this is my VT, this is my VS. If you write, okay, if you write VT dash, I'm taking the direction of current like this, is equal to Ri plus L di by dt plus Vs. Can I say that? If you take Vt dash minus Vs, it is simply this function. Now I want I is my output. If you take I on the right hand side, I of S, then you will get 1 by Ls plus R on. Why R on means there is some on-state resistance here. Let me consider this drop as 0, Vd 0. So there is something called R on. Because R is very small, let us consider R on also. So you will plus R on into plus Ls. This is your Vt dash minus Vs. So this is the transfer function with respect to my input. What I have the control here in this one is the modulation index M, which is your for sinusoidal now. Whatever we are giving, I said we are giving T. Suppose if it is sine function, we are giving two inputs. One is T, one is M. I already told you at the time of PWM techniques, by controlling M, like whatever the sinusoidal signal now, whatever you are comparing with sine, this repeating sequence. If you are controlling this M, your output voltage is going to change correspondingly, respectively, your current also will change. So I don't bother anything. Whatever that current that I have, that current, I'll take it as in feedback, and whatever the reference current that I have, that I'll choose this. Using that, I'll give it to a PI controller, and I will give it to this modulation index. If you just take only till this part, let us ignore the current. As I said, Vt minus Vds into MVDC by 2. MVDC by 2 is nothing but my terminal voltage. And if you subtract the source current, and if you divide by this, then you will get your I of S. Okay. Now what I want to inject a specific amount of current into the grid. See here, I'm not bothering about the model of inverter. I'm not going to bother about the inverter model. Here my plant itself is this one. 1 by Ls plus R on. So this is what I thought of explaining. If you just take this derivation, like M into VDC by 2 is nothing but your Vt dash, terminal voltage of the inverter, and Vt dash minus Vs is nothing but R, or you can dash R dash plus Ls into I of S. If you take the Laplace representation, or I. So if you want I, then you simply have to divide 1 by R plus R dash plus LS. Yes, R dash means R plus R LS plus VT dash minus VS. For this one, once I get I, now see, here comes the interesting thing. I have my I here. I'm sensing this I. Assume that I need a reference current 1000. So you can see this model in this control of voltage source inverters for power system applications. Sanja Kalijuka. If you have cascaded networks now, suppose you may have the T control, I control. In this one, that tuned value KP, KI, those direct equations are there in this textbook. You can see this textbook and you can get those values. Okay. But in the same textbook, this is the beginning part. So I'm just taking that reference and I'm explaining you. So if my reference is 1000 ampere, you have to give it. Here is my compensator. After my compensator, I'm getting some reference U. Actually, this can be your M itself. But see, I'm taking 1000 ampere and some current, some value, maybe like 280 or something 800. If you do this large value as an error to this PI controller, obviously your U value is extremely large. And this U, I have to make it into per unit by dividing with U by 2. Now what will I get here? I'll get this U by V by 2, which is a per unit representation. This always should be in the range of -1 to 1. Actually, for me, I have made it as 0 to 1 only. I have made it as 0 to 1. I didn't even make -1 to 1. For me, 0 to 1 is sufficient because my modulation index that I need should be between 0 to 1. Even I don't use 0 also, I'll use 0.6 or 0.5 like that. So 0.5 to 1. In this range, my entire network will work. So if you know once M, you'll give this VDC by 2, VT, and this is your half bridge converter. Okay. So once I get this network, once you develop this network, you have this representation. Once you get that, as you have got some closed loop, so you can tune this your KPKI value. Once you get this KPKI, you directly, whatever the modulation methods that you use, if you are using SPWM, you're always getting theta, and this modulation index M that you feed it here, this is going to compare with repeating sequence that will give you a switching sequence to these two. So PI controller, after the PI controller, you have to use that. So let us see the same in simulations. So this is my network. Here is my grid connected network. So I just want to open my MATLAB. SPWM and saturation block. How to model control logic. What do you mean by control logic? So this one. You are saying how to develop this. Okay, my voice is breaking. I think, is it fine now? My voice? See, how to develop this control system means you just have to apply the same network. This is actually a very basic model that we are getting I here. What we do is now, this is the basic mode. Like we'll get I reference here from this. Yeah, from this you will use a PI controller and you are going to get I. So this is one type of tuning network. But some people will do this I reference as ID reference and IQ reference. They will generate two block sets for the same network. Actually, I'm not explaining that concept. Like if you go for any PQ theory representation now, then you can explain that. So this logic is not specific. Here I am using 1 by ls plus r on. Some people, instead of using along with this, they will add an extra term, like that inverter is there, right? Whatever the inverter they have, they are going to take its representation as a first order differential equation, like e power minus ts something k into e power minus ts by 1 plus s tau. This ts is actually dependent on your switching frequency. This k magnitude is your VDC by 2, I mean the per unit value. This tau is again, they'll take it as this constants. So along with that, they will represent this as this constant. Okay. Sometimes they will take this representation instead of this 1 by ls plus r dash. It is up to you how you consider that model. Sometimes they will take this network separately, this network separately. Both of them, they will take both of them separate. Like you will have your converter as some first order differential equation. Your first order differential equation, and this extra term is there na RL, that they will add as a consecutive term. They will take this also as a separate first order differential equation, and they will take this one also separate one. So once you get this function now, and based on that, you have to first tune one after the other. Earlier, they used to give only current control. If it is a current control mode, this is called current control mode. Here I am giving I reference and I'm getting the output. So in this one, I'm giving current control mode, I'm getting it. But some people will sense output voltage and they will compare the output voltage in voltage control mode. So there are two things. In this textbook, you have that analysis. Control of voltage source converters for power system applications. Tanjana Kalijuga. Actually, whatever the compensator, whatever cascaded network compensators, that values also they gave. So you can directly place that if you are using some grid integration, and you can, I mean, if it is not completely innovative idea on that, then you can go for it. So that is how it's up to you how you consider your network. But if you approximate your network to some value, then you have to justify the terms, whatever the terms that you have. Actually, if I have more time now, then I would have explained. I should have done that extra simulation also. Okay, I just made this part of the simulation only to simulate about the basic view of grid connected inverter. That means it is not only this. If you can see that this is the actual representation of half bridge converter. Suppose I don't have filter, I have motor here. Then what you do is you have to have the state space representation of your motor, and you have to have a specific output Y. Here, this converter, you have to take it as first order differential equation. Just this converter, like you'll get e power minus ts, as I said now, e power minus ts. Why they take only first order differential equation? In steady state values, any plant can be realized using first order. You don't need any complexity. And even any industry, in order to tune the parameters, they don't want complex network for them to control the network. Suppose you have a big plant process. there will be a control room. In that control room, the people are going to adjust this KPKI values. I mean, based on some algorithm they have, they are going to adjust that. If they have this first order differential equation, there are some methods like Jigral-Nichols and IMUS, and even there is one latest method. So what is name? So that kind of networks can be easily implemented, and you can tune that KPKI value and you can get that output. So they don't want much complexity. They just know those, they will apply those Jigral-Nichols if they want. If these are dependent on planned functions, actually this tau, this is your switching frequency function. There will be some K function, which is again MVDC by 2 like that. That constant value, based on that, they're going to choose this. So that is like a first order equation, and there comes your state space variable function or your transfer function. For a given input, you consider that given output. Like maybe your input is modulation index M for a single phase, and you want some frequency omega, you have to find the transfer function for that. So once you find the transfer function and you apply the same PID tuning rule, whatever that we have here, that you can apply and you can get it. So if you see that network, can you see the MATLAB function? There is one more book, Voltage Source Converters for Power Systems. What is that? Voltage Source Converters for Power Systems by Yajdani, Yajdani. That book is very good. If you can, I mean, this is some part of that, even that. Voltage Source Converters for Power Systems, modeling, analysis, and design, something is there. So that Yazdani, instead of this author, you have Yazdani. So that you can use. If you read that book, then you can understand this, all these mechanisms, how they are approximating. But it is very old book, and currently no one is using that. But if you can understand this basic, and you have that your own transfer function, then you can use whether assume that your function is not properly known. What do you call? Assume that you cannot approximate this function properly. Then what you are going to use this, you are going to use model predictive control. If you can use model predictive control, then you are predicting its model and you can use that model somewhere. You can directly control the system without knowing the model. Or there is something called system identification. Even using system identification, you can track that network. So instead of this, you have some equations. You want the title of the book. I'll type. Yeah, Yazdani. Yeah, it is Yazdani. Yazdani. The same thing, voltage source converters for power systems. I'm typing in. But those methods we are not using now. Now we have, it's like, but industries, they are using only those methods. It's like always the research that we are doing, it has far predictions than the existing world. At a later stage, they may adopt that. So this book I'm saying, voltage source converters by Yazdani. So this book is also good. This is some part of it. This is what I have simulated in this. So what I did here is, I just did the same thing and I tuned this value. I gave that tuned value. I gave that tuned value here, PI controller. And see, as I said, we're getting that modulation index. Here I didn't use any PLL. I directly gave this value and I'm getting this V1 and T1 and T or S1 and S2. Here I'm using two sinusoidal signals. If you open this now, I'm using two sinusoidal signals. One is 2 pi f t, the second one is 2 pi f mt plus 5. Even you can use this form, or earlier I told you another form, no? Like you can detect that and you can directly give it. That also you can do. MATLAB window not visible. Is it visible now? Okay, okay. So that's what I did here is I tuned this using this linear approximation. Then I directly gave that PI controller here and I started controlling this. So I'll get reference M. T I just gave normally. I didn't use even PLL. So I just gave it normally just to test the system whether it is going to give the required output or not. Here my reference is current is 0, something like initially it has to be 0. After 3 seconds it has to be 1000. Can get the same thing. To simulate it, my current it has to be 0. After 3 seconds it has to come 1000. See, this is my call. If you see this, if you track this now, so the first one is your voltage, the second one is your current. That means yellow color is your voltage, blue color is your current. So this is how you get the thing. Okay. So you can try this. We'll see whether you can able to do that. I'm not showing anything. If you want, we'll see it tomorrow morning. I mean, in the beginning. Later on, we'll go for wind energy conversion systems, a brief view on that. Then we'll wind it a bit early. Then we'll have validity session. I'll make sure to complete it by 7:33. Actually, last time we have conducted for 3 hours and a lot of people have that issues. So we reduce the time and we have increased the number of days. But making 7 days consecutively for us is really difficult. Huh? We have to handle multiple things. Okay, if you have any queries, you can ask. When will be phase 2? Actually, we didn't even decide the topics for phase 2. We will ask you the topics of phase 2. If you can recommend something and if you are able to simulate that. Actually, we don't know whether we want to go for a hardware or we want to go for advanced nonlinear systems or we want to go for particle optimization methods. There are a lot of things. So we don't know what exactly we can go. The topics that we have chosen currently, these are the topics that was suggested in the first wave. I mean, there is one FDP that was happened in the month of April. At that time, we just gave the brief introduction of MATLAB. I mean, both in terms of power systems and power electronics. Some topics were repeated here, like in DC-DC converter, but I just told a bit advanced here, like PI tuning methods, along that how you have to realize the network. That is what I told here. So there, whatever that most of the people opted now, only those topics we have given here. Actually, we thought of choosing only one topic. We thought of explaining but 3. But as we can see, everyone is giving like all the things. So instead of explaining all the things, instead of explaining one thing in deep, it is easy for us to give the basic idea on all the things. So that is what we did now. If most of the people opted specific thing, then we'll give more time for that and we'll explain the things in detail. So we are not sure whether to go for non-linear control systems like model predictive control, sliding mode observer has a specific application, and or even cascaded tuning methods, optimization methods. Optimization maybe for solar PV systems that we can go, or even tuning methods we can go, or observers, controllers. This I didn't tell this concept. Deep learning on FMPPT. Why do you want deep learning? It is too much actually. Frankly speaking, it is. You cannot deploy deep learning in microcontroller. Whatever that ANN tool that you have obtained, I didn't find even a single route to deploy in hardware, because you will get a separate DNN toolbox that is entirely different. Or you have, if you need a lot of data to train your network, you're directly telling deep learning. Grid integrated inverters. I mean, deep into, is it SMPC? I mean, you're talking about model predictive finite. Okay. Switch mode power converters, advanced. Okay, that deep into SMPC. Okay, I'll give you that. I'll ask you the feedback. We can tell them. Based on that, we'll see the next topic. In electrical vehicles, what exactly do you want? So it's like whether you want to design the battery modeling, or you want to do fast charging. I mean, advanced converters with fast charging. There are multiple things. Or you want to control the motor. With respect to motor controlling in electrical vehicles, the network is already saturated. That means you will get everything. I mean, that is already a saturated area. Now it's like they're using deep learning to track the network. Like they are using IoTs, wireless networks. These are the things that are in current trend. I mean, you can see that industrial informatics papers and electrical vehicle papers and all these things, transactions I'm saying. We'll see, sir, even based on that majority options and based on our simulation practice that we'll give it in the next phase. But for time being, let us stop here. I'm sorry to take more than time. We'll see in tomorrow. If possible, I'll try to simulate this, then I'll go for wind energy conversion systems, or I'll skip this and I'll directly go to wind energy conversion systems. Okay. Thank you all for being patient so far. Jai Hind.